welcome to the part 1 of our next chapter, Due Nature of Radiation and Matter. First, we are going to discuss the photoelectric effect. We know that in metals, large number of electrons are moving freely about the lattice of the positive ions. We call those electrons as the free electrons. These electrons are free to move inside the lattice of the metal, but themselves they cannot come out of the metal because they are held inside the metal surface with the help of the electrostatic potential, which is called as a potential barrier, which does not allow the electrons to escape by themselves from the metal surface. So we need to give certain amount of energy from outside to remove such electrons from the metal surface. The minimum amount of energy which is required to remove an electron from the metal surface, we call that as the work function, or this energy is called as the threshold energy. We measure this energy in the unit of electron volt, and we know that 1 electron volt is equal to 1.6 into 10 raised to power 19 joule. And this work function value, it depends upon the nature of the metal, how strong is the potential barrier offered to the electron, and also it depends upon under what conditions the metal surface is held up. Now we can basically discuss 4 types of the electrons emissions. First is the thermionic emission. This is the emission of electrons by heating the metal surface. Emitted electrons are called thermions or thermal electrons. Second is the field emission. If metal surface is subjected to a very strong value of electric field, it may vary from 1 kilovolt per meter to 1 billion volt per meter. Under this strong electric field, the electrons can also be ejected from the metal surface, but this is a very dangerous method. Then there is photoelectric emission. If metal surface is illuminated with an electromagnetic radiation of sufficiently high frequency, even then metal can lose electrons. This is called photoelectric effect, which we will discuss now, and the electrons ejected are known as the photoelectrons. There is one last method that is called as the secondary emission. If we already have a very fast moving electrons, if very fast moving electrons are allowed to strike a metal surface, then these fast moving electrons, when they will strike the metal surface, they can also remove the electrons from within the metal surface. The electrons emitted in this way, ejected in this way, they are called secondary electrons, and this process is called as a secondary emission, because in this case primary electrons, they are coming from other source, their kinetic energy is increased and they are allowed to fall on the metal surface, from where they eject the electrons from the metal surface, called secondary electrons. Now we will discuss the photoelectric effect. We know that photoelectric effect is a phenomena of emission of the electrons from the metal surface when light of suitable frequency is allowed to fall on the metal surface. We call this as the photoelectric effect. This was discovered by Heinrich Hertz in 1887. The experimental setup to study the photoelectric effect is as shown in the figure, in which we have an evacuated glass tube in which 2 electrodes, cathode and anode, are present. Cathode is a photosensitive material on which a light of sufficiently strong frequency is allowed to fall on it by passing through a quartz window. Cathode and an anode, they are connected to a battery whose potential can be varied between the cathode and anode. We have also connected a microammeter in order to find out the amount of electric current flowing between the circuit, and there is a commutator arrangement also in order to reverse the potential difference of cathode and anode, so that their polarities can be reversed also. We can discuss the experimental study of the photoelectric effect by studying the various factors. The first effect is the effect of intensity of the light on the photoelectric current. As soon as the setup is completed and the source is allowed to fall its light on the photosensitive material, if energy carried by the light is greater than the work function of the metal, then it is going to eject some of the electrons from the cathode. If anode is kept at a positive potential, cathode is kept at negative potential, and anode is kept at positive potential, then as soon as the electrons will come out from the cathode, they will immediately be repelled towards the anode. The anode will be attracting them, and as soon as the electrons will start reaching anode, the microammeter present in the circuit, it will show the flow of the current in the circuit. Now, if we keep the potential difference between the cathode and anode constant, and we allow the intensity of the light to increase, then we will observe that as the intensity of light is increasing, the photoelectric current in the circuit also keep on rising. So if we plot a graph between photoelectric current and the light intensity, the graph will be a straight line as shown in the figure. This straight line graph shows a direct proportionality between the photoelectric current and the light intensity. Now, light intensity is actually the number of photons incident per unit area per unit time on the metal surface. The photoelectric effect is a 1-to-1 relation. That means one photon is able to eject one electron from the metal surface. So when we are increasing the intensity, we are actually increasing the number of photons incident on the photosensitive metal surface, due to which, as the number of photons incident are increasing, the number of electrons ejected are also increasing. That's why the photoelectric current is also increasing. So in this case, the photoelectric current is directly proportional to the intensity of the light. Now we are discussing the effect of the potential difference between the cathode and the anode for the different intensities but the same frequency. The graph is showing the variation of the photoelectric current with the potential difference between the cathode and the anode. Now, from the graph, if we are applying an accelerating potential, that is positive potential is applied to the anode, the value of the photoelectric current in the circuit first rises. Photoelectric current begins to rise, and after some time, as the voltage is kept on increasing, the curve almost become parallel to the voltage axis. This takes place because when all the electrons are ejected from the cathode, they are not able to reach towards the anode because they possess different values of kinetic energy. So the electrons reaching at the anode, they are lesser as compared to number of electrons ejected. So photoelectric current is lesser. But when collector potential, that means anode potential, is increased, then it even starts attracting those electrons which were earlier not able to reach at the anode. So photoelectric current begins to rise. With the continuous increase of the anode voltage, when number of electrons ejected per second, they become equal to number of electrons received by the anode per second, then all the electrons ejected, they start reaching at the anode surface. At this stage, there is no further rise of the electric current, so the photoelectric curve become parallel to the voltage axis. So at this stage, because there is no further increase of the photoelectric current, we call this current as the saturation current. So here we have the saturation current. So there the saturation or the constantness of the current takes place. You can also see that at even value of voltage is applied voltage is 0, there is some value of the finite current, and this current is more and more as the value of intensity is increased, because intensity means more photons means more electrons are ejected. So when even voltage is 0, even some of the electrons which have sufficiently large kinetic energy, they are able to reach at the anode without any accelerating voltage. So current even at 0 voltage is not equal to 0. Now if we reverse the potential of the anode with the help of commutator system, now anode is kept at negative potential, the photoelectric current begins to fall. Reason: anode, when it is at negative potential, it starts repelling the incoming electrons. So when it starts repelling the incoming electrons, at that stage number of electrons reaching per second, they start decreasing, so photoelectric current also starts decreasing. So at a particular value of the retarding voltage, negative voltage, the photoelectric current absolutely become equal to 0. We call this value of the retarding voltage as the stopping potential, which stops the flow of photoelectric current in the circuit. The value of the stopping potential, it depends upon the frequency of incident radiation only, because stopping potential has to work against the kinetic energy of the incoming electron. So what value of kinetic energy will be possessed by the incoming electron, that does not depend upon the intensity of light, but it depends upon the frequency of light. So if the frequency of light is greater, then the chances that electrons are ejected with greater kinetic energy, they are also larger. So in order to stop an electron with larger kinetic energy, greater stopping potential is required. So stopping potential depends upon the frequency and not on the intensity of the light. So the potential stops, this potential also is stopping those electrons which are moving with maximum speed. So using the energy principle, we can write down that the maximum kinetic energy is actually half mv max square, and it should be equal to EV0, where V0 is the stopping potential. So at the stopping potential, potential energy and kinetic energy of the fastest electrons, they are becoming equal to each other. From the curve, we also know that if we increase the intensity, the curve are always the similar, they have the same shape, but only difference, as the current intensity will increasing, the current will be rising due to the increase in the number of photons incident. Next, effect of the frequency of the incident light on the stopping potential. What is the effect of the frequency of the light on the stopping potential? Photoelectric current variation with the stopping potential for different frequency but same intensity. Now in this case, in the positive region, we can see only one saturation curve. Reason, because here the frequencies are different, but the intensity of the light is kept same, so number of photo incident are same, so number of electrons ejected are also same. So photoelectric current becomes saturate at the same value of the potential of the anode for all the three different values of frequency. But if we apply the retarding potential, you can see that as the value of the frequency is greater, so nu3 is greater than nu2, which is greater than mu1. In this case, as the frequency of the light is increasing, the value of the retarding or stopping potential is also increasing, because when you incident more strong frequency, you are providing more kinetic energy to the ejected electron. So in order to stop an electron with greater kinetic energy, greater electrical work has to be done, so retarding potential has to be increased. Now if we plot a graph between the stopping potential and the frequency of incident light for the different metals, the graph is as shown over here. From the graph, what we observe, if we look at the metal B first, the graph is a straight line, not starting from the origin but at a certain distance away from the origin on the frequency axis, like over here at the point X. This means that the value of the stopping potential at this value of the frequency is totally equal to 0. This indicates that when frequency is equal to nu naught, this actually is highlighting the minimum value of the frequency below which photoelectric emission will not take place, because all those frequencies which have value less than nu naught, they will have energy less than the work function of the metal, so they will not be able to eject the electrons. So the stopping potential is 0 for this value of the frequency. We call this frequency as the cutoff frequency or the threshold frequency. Now if you want to find out the corresponding work function of the metal, you just simply need to draw the straight line in the backward direction, and you have to find the intercept on the y-axis. So it is intercepting on the y-axis, suppose at this point P. In this case, this point P, it will give us the value of the work function of the metal. You just need to find out the negative value of the stopping potential and you have to multiply that with the electronic charge. So if V naught dash is that value of the potential at which the intercept is there, you will be multiplied with the charge on electron, so this will give us the value of the work function for the metal B. Same is true for metal A, which is having higher value of the threshold frequency. So as the value of incident frequency is increased, as the value of frequency is increasing, you can see the value of stopping potential is also increasing. So when the incident frequency is at this particular value, suppose nu1, corresponding potential is suppose V1. When the incident frequency is suppose it is equal to nu2, corresponding stopping potential is also V2, which is greater than the initial value. So as the frequency is increasing, stopping potential is also increasing. So from all of this, we observe some important points, that stopping potential is increasing linearly with the frequency, and there is existing a minimum cutoff frequency below which for which stopping potential is 0. We call this as the cutoff frequency. So when cutoff frequency have a 0 value of stopping potential, this means that no electron is able to reach onto the onto the anode inside the circuit. And if no electron is able to reach onto the circuit even with the 0 value of the stopping potential, this means that electrons do not have sufficient kinetic energy because they are not ejected for any frequency less than the cutoff frequency. If we plot this graph for two different metals, you can see from the graph it is straight line, but it is parallel. So they have the same slope, but the slope intercepts are different because they indicate different values of the work functions on the y-axis, and they indicate different values of the intercept on the x-axis, which indicate the value of the threshold frequency. So from this we conclude that maximum kinetic energy of the ejected electrons increases linearly as the frequency is increased, but it is not depending upon the intensity of light. If any frequency less than cutoff frequency is applied on the metal, no ejection is emitted possible. Reason? Because photon cannot provide enough energy so that electron can break the potential barrier and come out from the metal surface. So from all of this we can generate the laws of photoelectric emission, which are nothing but some highlighting point of the experimental observations of the photoelectric effect, which are that for a given photosensitive material and the given frequency of incident light, which should be greater than the threshold frequency, photoelectric current is directly proportional to the intensity of the light. That was the first observation. For a given photosensitive surface, there exists a minimum frequency below which no electrons can be ejected from the metal surface, no matter how strong is the intensity of light. We call this as the threshold frequency. Third, if incident frequency is above the threshold frequency, then the stopping potential, or what we can say, the maximum kinetic energy of the photoelectrons, is also directly proportional to the frequency of incident radiation. So as the frequency of incident radiation is increased, stopping potential as well as the photoelectric kinetic energy of the photoelectrons also keep on increasing. Last, the process is an instantaneous process. That means there is hardly any time lag between the light on the metal surface and emission of the electrons, and this time gap is less than 1 nanosecond. Thank you.